All right. So to understand chemistry, right? We are on the chemistry strand as of now, right? We've just entered this. Okay, so in the chemistry stand, now what we are working with is we're trying to understand the composition of matter, right? In general, that's the basic, you can say simplest way I can put this, that what's the composition of matter, right? So to classify that, I need to be able to make some measurements, right? So two measurements I would make would be one, the mass, right? And second, the volume. And this is how you define matter, right? Uh, Anything that has a mass and occupies some space, right? Do you understand me now? Remember, this is what matter is for you from the very beginning. This is what's been told. Okay, now I'm going to divide this matter into two different fragments. One is gonna be pure, right? Let me just make it a little bit bolder, right? So that should cut it, right? So this is the pure, right? And the other one is gonna be impure, right? And you'll understand why I'm using this color, right? Okay, now pure matter, right, is going to be only, our logic is going to be only one type of particles, right? Because we do know that all matter is composed of particles, right? We call them as atoms, we call them as molecules or whatnot. So we're going to classify what they really are, right? And then we're going to fix them up on the periodic table, right? And we're going to see how the periodic table is arranged and why is it placed in that way, right? So these pure metals can further be divided into two types, right? So I'm going to take one, right, as let me say elements, right, and the other would be compounds. Okay, now out of these elements and compounds, elements are the ones that exist as atoms of one type, right? Now there's a bit of a confusion here, right? A little advanced tip, that there are elements that exist as molecules, right? So it could be a lattice of a pure element, right? A sheet of metal maybe, right? The example could be iron sheet, right? Metal, which is lattice of atom of iron, right? Okay. Then we have sorry, we have monoatomic gases, right? And what monatomic means, single atom based gases, right? And the examples would be your noble gases, right? All of them, they are monatomic gases. Okay, all right. And finally we also have some what we call as diatomic gases, right? Diatomic, if the word is monatomic, then definitely there has to be something related to the count, right? So diatomic gases and more are there, right? In general, what we call as all of these, like diatomic and more of them, we call them all of these as molecular gases, right? Because whenever we're going to define in a moment that what's an atom, what's a molecule, right? We're going to define as atom, then we're going to define a molecule, right? The smaller particles. And then we're going to understand what is inside the atom as well, right? And then we're going to see what lattice is going to be for us, right? What is going to be a crystal. Okay, so these are the things we're going to talk about for just today, right? A small little thing we're going to talk about. Now if we go into compounds, we're only going to find particles or molecules, right? It's hard to find atoms in there, right? And why it's hard to find atoms? Because you don't have one type of them, right? So I can just, if I want to use the same strategy for this, I'm going to write instead this, right? Atoms of two or more types. Okay, all right. Now atom of two or more types, right? Whenever they join. Now here's the problem. Since there's a compulsion of having at least two atoms and they need to be of more than one type, right? Definitely, right? Two different elements need to combine together. So in this case, we are not going to have monatomic gases, right? That's going to be out of the game for one thing, because these are singular atoms, right? So noble gases cannot come here. They're not compounds, they're pure elements, right? Now we have molecules over here, right? But these are of one type only, right? One type, and that's the emphasis. So in this case, you can have diatomic or more complex molecules, but they are going to be only one type. So you usually going to find molecules having two different elements joining to form only one type of compound, right? Which is going to be found in the form of either molecules. We can find those crystals, right? Salts we have, right? Two different sodium and chlorine, two different atoms joined together forming crystals. We also have lattices, right, over here, but those are going to be not the elemental lattices, right? These are elemental ones. These are now compound based lattices, right? And eventually you're going to find gases and liquids, right, of different sorts, right? Over here you can also have liquids, right? For example, you have bromine gas, right? That's a molecular diatomic molecular gas, right? So that gas or bromine, you can say, is found as generally as liquid, right? So that is going to be entirely different from what a compound is, right? So these are there, but remember, two or more types of elements need to be there, right? Types of atoms are going to be there. Now these are going to be your compounds, right? So if I write the example like oxygen gas over here, right? That's an elemental gas. You have neon gas, right? Then you have steel. Oh, sorry, not steel, but should I say iron, pure iron, right? So you have iron, right? Sheet or iron piece, right? Solid iron in any way, right? That is going to be there. Those are elemental. You also have liquid mercury, right? Liquid mercury. It's a metal, but it stays as liquid form at room temperature, right? Very dense metal to work with, right? And very poisonous one as well, right? So these are pure elements we're talking about, right? Because they if you look at them, if you look very deep into them, you're going to see that they're only made of atoms of one type, right? When we have compounds, we have NaCl, salt, which is a crystal, right? Then for a liquid we have water, which is also a compound, right? If you pick up a glass of water, pure glass of water, it is only going to have water molecules with it, right? I'm just depicting these. I'm gonna take you to the lab and build these molecules as well for you, right? And show the 3D features as well, right? So this is sodium chloride, water, right? We've got HCl, which is an acid, and then you have other gases, right? Ammonia, which is kind of a gas, low melting liquid, you can say, right? And you have sulfur dioxide, carbon dioxide, right? So these are gases. Now oxygen gas, the one that we breathe, is elemental because it's only having one type of atoms, right? Well, one is an oxygen combined to another oxygen. In this case, there are two different types, right? One carbon, one oxygen. That is going to be a compound, right? Okay. Now we're going to go into the impure version, right? These were having, like, if I take a container, put either of these independently, right, then I'm going to find only one set of molecules, right? That is going to be just pure one type of that form, right? Whether it's a crystal, lattice, gas, liquid, or just molecules as well, right, of a gas, it is going to be only of one type, right? Not pure elements, but still one type, right? Now impure, as the color suggests, is the one that is going to have a different approach to this, right? For example, if I divide impure, there I'm further going to divide it into two as well, right? So one is going to be your solutions, right, in which you take more than one compound, right, or element, right? In that case, you mix them together and they're equally easily distributed, right? Very well distributed. So two or more, you can say, types of uh, pure substances, should I say, right? To be more exact, substances, right? Now that is what solutions are for you, right? Now solutions could be of several forms. For example, your tea is a solution, so it's very well mixed, right? The tea ingredients are mixed very well with milk, and you get that brownish shade all over the place, right? So those are solutions. Then you make any juice, right? Let's say quick sachet juices, right? So you just pour that colored salt in there, and you get a colored solution in there. So in that case, if I just draw uh, a schematic of it. So let's say if there's one compound, this orange one, right? That is one chemical, maybe a liquid we're talking about, right? And the particles are spread all over in this container. And there's another one, which is like another juice, or maybe water molecules along with the juice particles, right? So they'll be very well mixed. Now this is what you call as a solution, where the properties are what we're going to call as homogeneous, right? That means they are consistent, right? So now for impure, we're going to have mixtures, right? Okay, now for mixtures, we're going to have two or more substances again, right? Two or more types of pure substances, but this time not able to settle together, right? Now in this case, right, in this case we're going to have a different version of the same uh, container, right? Let's say two of them. One is this orange, right? It's just sitting right there, let's say sand particles, right? And then you're going to have water in there, right? It's filled with water. So what you see over here is that these two substances which are pure, maybe water is pure, like it's a compound, and sand is another compound, which is SiO2, right? So if we have, let's say, water, H2O, and we have sand, which is silica, right? SiO2. If we try to mix them together, no matter how many times we try to shake them, eventually it will settle down and they'll be separate, right? So you see, by settling, I should say, not staying together properly, right? You can say more to make it more easy to understand, right? Able to stay together, right? The way they are staying, right? These are able to stay together while keeping a consistency in their distribution. Now these are called homogeneous. So on the contrary, these are going to be named as heterogeneous, right? So heterogeneous are substances which are not able to mix together, right? They're going to have different properties at different level. So let's say if I take a sample from here for water, that's going to be different composition. If I take a sample from here, you're going to get water and some of the sand. But if I just scoop out the very bottom of it, so you're going to only find sand and very little amount of water, right? Now that is what you call as heterogeneous. And if I take the sample from here and here, there's a probability that I'm going to have similar composition, right? For each, right? If I just add another green in here just to make it understandable that this is going to have a more consistent behavior compared to the mixtures, right? Now these are the basics of what we understand, right? So eventually it comes to just atoms or molecules at the bottom end, right? That's the framework. So let's define atom, molecule, and crystal lattice, right? Uh, so atom, what's an atom, right? It's the smallest uh, indivisible, right? Please don't mind my writing, right? Indivisible particle of matter, and we're talking about matter right now, right? Pure ones and impure, all of them. So that's what an atom is. A molecule, right? When two or more atoms join together, right? They form a molecule, right? But that could be number one, right? Elemental molecule, that means atoms of only one type. For example, O2, which is oxygen gas, sulfur 8, it's going to have 8 atoms of sulfur, all of them together, right? And then you've got like O3, which is ozone, 3 atoms of oxygen together, right? And then we have the number 2, which are compound, right? Compound molecules. That means they're going to have more than one element being joined together, right? Compound molecules we're going to talk about, and that is going to be like NH3, which has nitrogen and hydrogen joined together. Then we have H2O, water, right? I've given you examples as well. Now these are molecules. These are compound molecules, and these are elemental molecules. So we are going to consider those as elements, and these as compounds. But the particles for them, the smallest indivisible particle we're going to find them as pure, is going to be a molecule for both of them, right? So keep this idea in mind, right? That atoms exist as like elements will mostly exist as atoms. Some of the elements also exist as molecules as well, right? But mostly compounds will never be able to exist as atoms, right? Because they are impure. No, not impure in a way that they're the combination of more than one element, right? So now what is a lattice, right? It is a repetitive arrangement of particles, right? And that could be for you can say number one, elements, right? And number two, also for compounds, right? So both can exist as lattices, right? Repetitive arrangement of particles. Now for atoms it could be atoms, right? Or it for compounds it could be you can say ionic compounds, right? We're going to know about what these ionic compounds are, right? I'm just going to give the idea that these could be compounds, right, alone. And I'm not going to use the word molecule, although for Cambridge they do use the word molecule over here, but I'm not going to call them as molecules. I would rather use the word ionic formula, right? Compounds that have an ionic formula, right? They're going to exist as lattices, and those lattices, when they grow up into a larger structure, what we call as crystals, right? So we can say the larger physical structure formed by lattice, right? And that is what you see as a crystal, right? If you look at a salt crystal, right, a very cut piece, right, it's a needle-like crystal, salt crystals. So these needle-like structures inside, they're made up of these repetitive arrangement of atoms we call as lattices, right? It could be like this, right? If I take, so the atoms are very well arranged, very close to one another because of the crystals, they're solid, right? And metals can also exist like this, right? So if you pay close attention to metal sheet, some of the metal sheets you find across, in the market or anywhere, right? In any construction zone, if you're crossing, you find that some of those sheets have textures on them, right? And those textures are basically, if you look closely, if you have a microscope, then you'll be able to find that those are lattices, right? Big structures created by atoms. Now you won't be able to see the atoms, but you'll be able to see the arrangement in the form of these lines or scratches, right? So they each one is going to have their own combination, right? So you'll be able to see some finite, especially more visible with the element tin, right? Mostly used in areas, you can say, for the wavy metal sheets you must have seen, right? With randomized texture on it, right? So I can show you an example of one of these, right? So this is what we understand just by matter, right? How we can classify matter, right? Now the problem is when we talk about pure substances, right? So we have a huge number of distinct materials that behave differently from one another, right? And those, now we're going to come to the point, what are elements, right? So elements, as we suggested, only one type of atoms, right? Those are elements. So these elements, they are in a huge quantity, right? We have discovered so many of them. So we wanted to arrange them, right? So we wanted to create an arrangement that could help us understand the behavior of elements and relate them together, right? So that is what we called periodicity, right? And periodicity means uh, repetition of uh, behavior, you can say, right? In general, right? How the materials behave. Let's say if it is an aluminum sheet, right? Why you can easily shape it and move it around. And then you have copper, right? That is also able to do that. But if you take an iron sheet, right? Iron, right? Then iron is going to be a little harder to shape around, right? It's gonna be way harder compared to copper and aluminum. They are soft, they are more malleable. Iron is also malleable, but it takes a little more force than usual, right? Then you have metals like titanium, right? And these are going to be exceptionally hard to turn around, but they're as light as aluminum, right? And then you have tungsten, right, which is even heavier than iron and very much impossible to shape into any articles, right? So these are distinct properties, right? So we also know the metal sodium, right? Sodium represented by this chemical symbol Na, right? So we're gonna learn about what these are as well, right? So then we have lithium, right? You know about lithium because you have lithium batteries in your phone, right? That battery contains this metal in there, right? And then we also know many of the elements like oxygen, the one that we breathe, but this is in gaseous form, right? Unlike these, which are metal, which are lattices, this is existing as molecules, right? So we then other gases are there like chlorine, right? Nitrogen. So what their behaviors were, right? They were all different from one another. So we wanted to create an arrangement that will help us understand them easier and relate to each other, right? For that we created the product table, right? So the general shape that you see of the product table, right? Like this. I'm just gonna go with a few blocks, right? For the beginning, right? So this there we have hydrogen, then we have lithium, then we have beryllium, right? And then all the way across there are 10 of them, right? 10 metals, right? I'm not gonna draw these ones, right? Because these are called transition elements, right? We're not gonna study those for now, right? Because these are more complicated than the ones we're gonna talk about. Okay. Then you have about six more, boxes over there. One, two, three, four, five, and then the six, right? I'm just gonna go a little straight up here. Okay. Now I'm just gonna talk about this set, right? So far. So we have this hydrogen placed here. Then we have the gas helium, which is a noble gas, inert gas, right? And then we have boron, we have carbon, we have oxygen. Sorry, we have got nitrogen. Sorry, right? And then oxygen, right? So we've got nitrogen, oxygen, and then fluorine, and then neon, right? And why these are placed like this, what is the meaning of this arrangement, we're going to talk about that, right? Now follow me on this, that you have two ways or two arrangements in this kind of format, right? Let me just draw the other boxes so that just the boxes, I'm going to fill those up later, right? Talking about what they are and how they're behaving, right? So I'm just going to pull these lines down for now, and I'm going to keep them empty. I'm going to go with these two as well later, right? These I'm not going to talk much about, right? Just these, right? There are 10 10 metals in between. We're not going to talk about those as well, okay? These are like a whole block of them. So over here you can see uh, an arrangement which is vertical in nature, right? You see vertical arrangement, right? And then you also see a horizontal arrangement, right? So in this case, in both these cases, you are arranging the elements, like you can see, you can read it this way, right? As the arrow, the orange arrow goes, right? Or you can go downward as well, right? Now these are arranged in a manner that usually when we talk about the properties, general chemical behavior, right? If we talk about the chemical behavior, because this is chemistry strand, so we're concerned with chemical behavior, right? For now. So with the chemical behavior, we're going to find that the elements which are common to be arranged together, they are going to be down, right? This is what we call as groups, right? So these vertical configurations are called groups, right? So all of these are groups, right? And we can number those groups, right? 1, 2, right? There are again from 3 till 12. We've got these 10 metals in there, right? Then 13, 14, 15, 16, 17, and then 18, right? Now these are called group numbers, right? I'm just gonna box them so they're prominent over here, right? Now these are called group numbers, right? Okay. Okay, another arrangement that is there is going to be your orange word, right? In this direction, right? The horizontal array. So we can number those horizontal ones as well, right? So that's going to be 1, line 2, line 3, line 4, right? Okay, I'm just going to remove this and I want to get back to this. Okay, now I'm going to write a number on these, right? I'm going to start counting from this one, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Right? Now these are the first 10 elements in your product table, right? And the number continues, right? It let's go from 11 is going to be 12, right? Then 13 is going to be like, sorry, this block is like underneath this, right? The transition will actually start from below this, right? After this, right? There's the transition metals, right? Okay, so then it's going to be 13, 14, 15, 16, 17, 18, 19, and 20. Now these are the ones you should remember. You're going to get to know them, you're going to use them, and you will learn about all their reactions, how most of them are mixing up together, forming different compounds, how elements are being formed, elemental gases are there, right? So we're going to talk about these. Now these are groups, right? Now if the period is there, so this is the one horizontal arrangement, right? I should use the same color as the numbering, right? So this is going to be your period 1, period 2. You're going to read them in, as such, and every time you reach the end of the period, you have to go downwards, right, into the next one. So from there you're going to return back to the first one, right? So from there you're going to go to the next line. So I'm making this arrow, right? So you're going to start counting back from there again, right? And then the transition metals are going to be there, right, from 21 to 30, right? uh, and these 10 are going to be there. Then it's going to be 31, 32, 33, 34, 35, and 36, right? We're not going to talk about these, right? I'm just writing numbers so that you understand. We have uh, placed these elements in the increasing number, right? In an increasing number. And why these numbers exist, this is what we call as the atomic number, right? And what the atomic number represents, it represents the number of protons an atom has, right? Or the element in that matter, right? Because elements exist as atoms, right? And the second one we're going to talk about is going to be your atomic mass, right? Which is the sum of protons and neutrons, right? Also known as nucleon number, right? So remember these names, right? Now these are the two things we're going to talk about. So what these protons, neutrons are, right? And how we are arranging those elements, why I arrange them. So we're going to look at the structure of an atom, right? So how does an atom look like inside it? So atom is basically a small little round nucleus, right? Which has, let's say for the hydrogen, it is going to be plus one, right? One proton, right? And one neutron. And neutrons actually have zero charge, right? They don't have any charge on it, right? So if I take this, or let's say if we talk about the helium atom, it's going to be two protons and two neutrons, and eventually it is going to have these negative charges on the outside we call as electrons, right? So you have known a little bit about these charged particles we call as electrons, right? These are negatively charged, right? And then we have the positive particles in there. Let me just draw those properly, right? In the form of let's say red, right? It should be red. So one proton, second proton, right? And then I'm going to go with the green one for the neutrons, right? So there's one neutron and there's second neutron. Let me just give it the correct. Oh, all right. Electrons are supposed to be blue, right? Let's draw them with this blue. Now electrons don't really have much mass, right? They have very low mass compared to other particles in the atom, right? So this central part is what we call as the nucleus, right? It contains protons, which are positive, and neutrons, right? Which are neutral, as the name suggests, right? They don't have any charge, right? So atomic mass, as suggested, right, was basically the sum of the number of protons, we're going to represent it by Z, and the number of neutrons we're going to represent by N, right? So your atomic mass represented by capital A, we're going to use this letter A to represent atomic mass. It is going to be Z plus N, right? Now this is your atomic mass. And if I just talk about the atomic number, right, in that case we're just going to talk about Z, because we just defined that the atomic number is the number of protons an atom has, right? So that is going to be your Z. All right. Okay. Now in this case, we are done understanding what atomic number and atomic mass is. We're going to talk about electrons very later, right? Because this is related to, you can say, all of the chemistry is revolving around these electrons actually, right? Because the electrons define the chemical behaviors, right? We're going to talk about them later. First, we're going to see how this these two informations, right? These two pieces of information are going to help us arrange the elements so that they are having similar chemical behavior, right? We're going to talk about electrons at the end. We're going to relate it to electrons, right? So imagine these are the atoms. So just by the look of it, it's got two protons, right? Two protons, two neutrons. So the mass is 4, right? And it's got two electrons, which is balancing the charge. So the atom is neutral in nature, right? So every atom, to be stable, needs to be neutral, right? So it is neutral because all the positive charge is equal to all the negative charge in the atom, right? And the neutrons have none, so they equalize. All the positive and negative should be equal, okay? So we once started discovering element, we identified them. Some of them were having similar behavior, right? For example, lithium and sodium over here were having similar behavior. For example, if I take a piece of sodium, put it in water, it's going to catch fire, it's going to, bubble out very vigorously. It's going to be a violent reaction. If I do the same with sodium, it's going to be the same result, right? And it's going to be same for potassium, right? Represented by this chemical symbol K, right? Okay. Then later we found some metals like magnesium, right? Very common metal that do bubble in water, but the reaction is not as vigorous or not that exothermic in nature, right? It does not explode. Potassium literally just explodes in water, right? Because this behavior was common in them, right? So let me just choose a lighter shade, right? So we're talking about this group, right? Hydrogen, on the contrary, is a bit different from there, right? So I'm just gonna shade, mix shade hydrogen for now, right? I'm just gonna mix shade it, right? Now this is part of this first group, but it is a bit different from rest of them because they are metals and hydrogen is a gas, right? Okay, but we're going to find similarity as well in the behavior, right? So magnesium did bubble but did not explode. Same did calcium, right? With a little bit hot water, did not react with cold water that easily, right? But both of them started bubbling in water. So we found that these metals, right, had another common behavior, right? So we wanted to know their properties, and that's why we calculated these masses, right? And then we arranged them, their increasing number of protons, right? So that means hydrogen is going to have only one proton in it, right? Helium is going to have two, lithium is going to have three, beryllium being 4, 5, 6, 7, and continues all the way to the total elements discovered till 9 are just you'll be amazed to know that they're 119 actually, right? I've just written 20 of them, right? So that are arranged in a manner where the properties are repetitive. So over here the properties are repetitive, over here the properties are also repetitive, right? And same is gonna be here, 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 and here, and here, right? So if I have argon, right, then this is going to be here, right? Because argon is a noble gas. It is not reactive. It is going to be as inert as neon and helium, right? So all three of them, and furthermore, right, all the seven noble gases, right? They all are inert. They do not react. They're very stable. Compared to that, if I talk about group 17, it is going to have chlorine underneath it, right? Both of them are poisonous gases, right? They're reactive gases. They exist as very light gases, right? So they have similar behavior. Then we have oxygen, that we breathe, and then we have sulfur underneath it, right? We do find sulfur. It is sort of poisonous, but in general, it is found as elemental form, right? Just like oxygen as a non-metal, right? This is not a metal, right? It is a powder, but non-metal, and it easily melts, right? So it's a low melting solid. Now underneath nitrogen we have got phosphorus, right, which also exists as a gas, right? It is also slightly inert like nitrogen, does not react that easily, right? And then underneath we under carbon we've got silicon. Both of them are very strong structures, right? Like carbon, which is diamond, right? Very strong. Then we have silicon, right? Silicon wafers, which are very strong, just like as sharp as diamond, very shiny as well, right? And then under boron we've got aluminum, right? Now over here aluminum is, although on the contrary, I'm just gonna uh, you know box it out, right? It's gonna be a little different behavior, right? Because that one is a metal, and the ones I'm gonna highlight in now yellow are going to be your non-metals, right? And that is why we just study this much of your uh, periodic table, right? Now these are all non-metals, although I'm just gonna shade this section of this in a moment, right? Now these are reactive nonmetals. These I'm just gonna change the color a little bit more, right? I'm gonna make them pink, right? That these are least reactive, right? These are noble gases, hence they're pink, right? So they are separate. These are your gases, right? I'm just gonna take out this. Oh, sorry, right? I'm gonna take out the color from here and here. Okay, I'm just losing these. Okay, now this is going to be boron and carbon. I'm going to give them another color, right? Just to signify that they're even something different from all of these, right? So I'm going to take light gray, right? And I'm going to fill that up. These are called metalloids, actually, right? And why these are called metalloids? Because they have behavior that is in between both metals and non-metals, right? These are the most special elements in the whole periodic table. Trust me, rest of the periodic table is simply boring, right? Majority of the usable compounds, all the things that we see around us, life, living animals, inorganic, bottles, screens, cars, anything, they are mostly, majority of them, and few of the metals, right? Few of the transition metal common ones. I'm just gonna name them, like iron, right? Like Fe, copper, zinc, right? These are like common ones. Silver, gold, right? Platinum, Pt. So we come across these majority of the metals, which are most abundant metals on Earth, along with these elements, which are also very abundant, right? Rest of them are there; they're abundant, but they're not much very useful, right? At least not in large quantities, like these elements do, right? Now these are arranged in the increasing order of their atomic number, and the behavior is actually repetitive down the group, right? So if, let's say, if I have fluorine, then underneath fluorine is going to be your bromine, right? Br. I was talking about that, right? So bromine is also poisonous. It is brownish gas. Even the colors are related, right? So fluorine is very light green, whitish green. Chlorine is very toxic blue, toxic bright green, right? And then we have bromine, which is brownish yellow, right? And then we also have iodine, which is purplish brown, right? So their colors are related, right? This group, right? So I'm just gonna pick out three groups, actually few of them, right? And I'm going to talk about them independently, right? And we're going to name them, right? Just for the sake of ease, right? So we're going to name them in a way that number one group, right? is what are we call as alkali metals, right? These are metals which are alkali. Hydrogen is the exception, right? Number two, right? Number two group, we have alkaline earth metals, right? Right, mostly found in earth as well, right? In some solid form, right? In some compound forms. And then we had number 14, right? I highlighted that. Those are called metalloids, right? And why we call those as metalloids, we're going to talk about them. Then I picked up 16, which was of my interest, right? I'm gonna give it a name in a moment, right? First, I'm gonna go with the next one, 17 and the 18. And you know about the 18, which are noble gases, right? Sorry, noble gases or inert gases, right? And we have this 17 we call as halogens, right? And above halogens, I mean, along with we have number 16, which are chalco, uh, sorry, right? CO gens, right? Chalcogens, right? Uh, the namingly, I'm just gonna give some of the metals: sodium, lithium, potassium, right? For alkali, we've got beryllium, magnesium, right? Calcium, and then for metalloids, we have carbon, silicon, chalcogens. We've got oxygen, sulfur, right? Chlorine, bromine, most common that we use, fluorine as well, right? So all of these, iodine, these are the elements I would advise you to get to know, right? And then we have got noble gases, which are like helium, neon, argon, right? And krypton, Kr, right? uh, radon as well, right? Ra. So all of these are very important ones that we talk about. There's like 15 as well, right? I missed 15. You can put the 15 in there, but these are the names that you should remember in your course. As of now, for now, you'll work with the alkali, right? Alkali metals, the alkaline earth metals, right? uh, and then you're going to talk about metalloids a little bit, and halogens, and noble gases a little bit about, right? And mostly you will study the reactions of these 1A, 2A, and this, right? We're going to talk about other reactions later on. Out of this, this carbon is going to be more important for us, right? Oxygen here, and we're going to have chlorine, most common, right? And from here, sodium, we're going to talk a lot, right? These are the ones I'm talking about. We'll talk about a lot, right? And then we have hydrogen as well, right? Somewhere alone. And we're going to talk about hydrogen, how hydrogen with all of them works around, right? Now, this is the brief of the periodic table, right? How the periodic table is there, what is there, and how they are arranged, right? How, what is the vertical arrangement and the horizontal arrangement along the rows, right? The horizontal arrangement, the atomic number increases, right, till it reaches the end, then comes back down, and then keeps on increasing till, I mean, you reached 119, which is the last element that we have found, right? So this is the arrangement. Any questions so far, Ayan? Anything? None, right? Okay. Are you able to classify, chemicals as elements, compounds, and how they are arranged as elements in the periodic table? Are you able to understand these things now? Okay. Have you talked about the physical behavior of matter as well? Not that much in the class. Okay. So, um hmm. All right. Okay. Let's get with the new page, right? I'm gonna start over a new page, and we're gonna talk about the kinetic uh, behavior of matter, right? Also known as the kinetic theory of particles. Have you heard about this? Oh, come on. We have done this before. Yeah, we've done this, right? Okay, I'm just gonna give you a refresher, right? So we've got solid, we've got liquid, and then we're going to have gas, right? All right. Now these are the three states of matter, right? Now how physically they appear, like as a rigid object, or as a flowing object, or as an invisible object, right? Pretty much invisible. Or you can say, in terms of, we talk about their shape, right? And their flow as well, right? So what we expect from there, right? So in terms of solid, what's the shape? Fixed or not fixed? Fixed or not fixed? So it is fixed. Okay. For liquids, fixed or not fixed? Not fixed. Okay. And for gases, not fixed. Okay, we're going to make a little matrix, and from there we're going to drive our kinetic theory, right? Okay. As for the flow, can the solids flow? Nope. Right? No. And so liquids, so they can. And gases, normally, yes, obviously they flow in and out of your lungs, don't they? Right? So gases do flow. Okay. Now this is the flow and the shape. Now this is only possible if we talk about particles, right? If we just go too deep into the viewing of these states of matter, let's talk about water, right? Ice. So what we're going to find, that the particles are fixed and they're not able to flow. That means we can predict that the particle behavior is going to be either that the particles are not able to move around, right? They cannot move about, right? Okay, that's point number one. And number two, what sort of movement is going to be there, right? If they're not able to exchange places, let's call it, right? More appropriate would be uh, not able to exchange places, right? They can't. So generally speaking, if they are not able to exchange places, then what sort of movement is going to be there, right? Because if the particles are not moving, then the matter is not going to be unstable. It's gonna rip apart, or whatever is gonna happen to the atoms. So things keep on moving, right? So what kind of movement is going to be there? We're going to call that as vibratory motion, right? So they're going to have vibratory motion, the particles, right? And we represent it like this, right? A particle going up and down. So if you see particles having this kind of representation in any figure, that is representing that this is vibratory motion. Okay. Now let's talk about liquids. They can flow. So what do you predict now for liquids, right? I gave you the prediction for the solid. Sorry? Use the similar word. Yeah, they're able to. They're able to exchange places, right? They're able to exchange places. Okay. And on top of that, right? If the gases are flowing, I think that is going to be the same way, right? Isn't that so? Because they're also able to flow. So we can relate this to gases as well, right? So the particles can exchange places, right? Okay. So let's relate their movement. So what kind of movement? You do know that liquids are a little bit more dense compared to gases, which you cannot store in. Let's say if I ask you to form a bowl with your hand, right? And you pour some water in it, a few droplets of water, they stay in your hand, right? But I doubt if you try to hold gas in your hand, it's gonna stay in your hand. Is that so? Is that's the general observation, right? Hmm. So what kind of movement would you expect between the gas and the liquid then? So they have spaces between them for which liquids or gases? With spaces, you're saying, right? With spaces between them, and then gases have huge spaces between them. Yeah, huge spaces between them. Okay, good. So what kind of movement do you expect them in both? Okay, random motion we call it, right? Because we cannot classify that. That's going to be random motion, right? In this case, the movement is going to be restricted, right? But it is going to be random, right? It is going to move. The particles are able to exchange their places, okay? So over here, this is also going to be random motion, but I'm going to call it high speed random motion, right? There are very high speeds compared to this, which is going to be slow random motion, and this is fixed, so they're just vibrating, not moving at all. They're not exchanging places, right? So now this is how we describe matter in its three states in the form of particles, right? This is what we call as a kinetic theory of particle, and this explains the behavior of particles. Now whenever I'm going to relate, now one thing I'm going to relate over here is going to be temperature, right? One variable that I'm going to introduce over here. Now this is a variable. Variable means something that I can change, right? So what if I increase the temperature, right? For all three of them. So what are you going to see is that the particles which have this motion in them, right? They have motion, so they have energy, right? So the energy of particles would increase, right? And this energy that I'm providing is in the form of what we call as heat, right? Thermal form of energy, right? Thermal energy or heat energy, right? So I'm providing them heat. Let's say I have a bowl in which I have like three beakers. One has a solid in it, right? Which is not having a lid, so it's a solid. It's put in there. Then you have a liquid, right? Which is there, and for the gas, I unfortunately have to close the beaker as well to allow the gas to be in there, otherwise it would just escape, right? So these are the three forms in which we're going to see the particles being like this, as we has predicted. And in this form, right, the particles are far more well arranged, but they're not able to move about. So we don't need a lid for this, neither for this, but for this we need to have a lid there, right? And why? Because it would escape. Okay, it's closed. Now if we give it heat, we will see that their speed, they're going to gain energy, and they're going to have faster movement, right? They're going to have faster movement up to a point that these particles will start to collide with one another nearly, right? And they're going to energize each other, right? They want to now run away from one another, and that is when we're going to see a phase change, right? So if we start increasing temperature of ice, it will eventually turn to liquid. It would melt and turn to liquid water, and then eventually if we keep on heating it, if it's going to boil up and it's going to turn into steam, which we call as a gas, right? So over here we can now discuss the particular behavior of these forms of gases, right? Not just like kids that you've been doing so far, right? Now this is going to be a little more advanced, because as you're going to the lower secondary, you're going to understand the particle nature as well, right? Why these are happening and what is the particle behavior at one point, right? So if you're heating it up, right? I'm gonna use orange for heating, right? If you heat it up, right? So what happens to the particles, right? And what we call this, right? And if you cool it down, now in this case, let me just choose cold blue color, right? So if you're cooling it down, then what's gonna happen, right? If you just cool it down, right? This is a cooling cycle. So I know you know this, right? This is what we call as melting. Okay, right? Let's use a color as well, right? For that case as well. Okay, this is gonna be melting, right? And this is going to be boiling. Okay, and the way back is gonna be your uh, condensation, and finally you're going to have freezing. All right. Now these are the things. Now what the particle behavior is going to be when they're turning from solid to liquid, right? Particles loosen up and start to move away from each other. And why is that so? Because let's say you've got two particles which want to vibrate, right? A point will come that they will not have enough space to move about, right? So that's when they want to get away from one another to have more space to utilize the energy that we're giving them in the form of heat, right? And dissipate that energy in more motion. So they'll start moving about in their places, right? So that they're able to create more gaps. So that will we are going to see kind of melting, right? That means it would start turning into liquid, right? And then eventually from this, we're going to see that particles have gained enough energy to break free, right? Break free. And why break free? And that is the very reason I put this lid on the container, right? Because if for liquid, that it's not escaping, right? It is able to flow. It is not fixed, right? It is not like a solid. The particles are able to move about. They have random motion. They have slow motion, right? That's fine. We can heat it up to make it a little bit faster. But unlike the gas, I don't need to put a lid there, right? This is not gonna escape. But in this case, for the gas case, the particles have taken so much energy now that they break free from one another and move away, right? And that's and move away from each other, right? That means now they're going to be very separate from one another, right? So if we start condensing, that is going to be the opposite behavior, right? The particles have lost their energy and now they're coming together loosely, right? So we can say particles have lost energy and came loosely close to each other, right? And then in this case, they have particles have lost enough energy, right, to be stuck together. That is going to be a solid, right? Again depicting vibratory motion, right? So Ayan, you're here with me, all right? Okay. Now this is the particle behavior that you need to now discuss at your level, right? Now this is not grade 3 4 where you can just call it, right, it's boiling, the it's gaining energy and it's turning into a gas. That is for kids now, right? Now you're in the lower secondary. Now you should be able to use the word particle, right? And the word this statement of how these particles are arranged with one another, right? In solids, they are very well arranged, right? That is why they are fixed, right? Shape, right? And for liquids and gases, they are not very well arranged. They're misplaced. For gases, it's actually violent in nature. They collide with each other, right? Very violently. So these can be explained in terms of the particle theory as this, right? And eventually we can relate all of this to the product table and how some of the elements are existing as gases, some are liquids, some are solids. That's why we're discussing this background as well, right? In particular form, because over there, if you reckon, right, we were discussing elements and compounds as particles, right? So we want to understand the behavior using the idea of the particle nature of matter, right? Are we clear so far? Yes? Okay. Now I'm gonna make something odd for you, right? You must remember this, right? You might remember this. Probably would have done sometime long ago, right? So from solid to liquid, there is one transition. From liquid to gas, there is one. From gas to liquid, there is one. From liquid to solid, there is one, right? Yeah, you can name them, right? So this is melting, sorry, right? So I'm just going to use the right one. Not evaporating, melting and boiling. My dear, we're going to talk about boiling and evaporation as two different terms, right? This is like state change forced by us, right? Forcibly, right? We are forcibly changing this, right? This can happen naturally as well, but the point at which all of the liquid is going to turn into all of the gas, that is going to be boiling, right? Evaporation is very different from boiling. We're going to talk about the difference as well, right? So this is going to from gas to liquid. It is going to be condensation, right? Condensation, and then we have freezing, right? Now what I want you to identify are these, right? From solid to directly into gas. What do you call this? Hmm. Yes, sublimation, right? You remember this. Okay, this is sublimation. And from gas back to solid. That is called deposition, right? You deposit a gas particle directly onto a solid form, right? So that is called deposition, deposit, right? To deposit a gas, you cool that so quickly that it turns into a solid rather than going through the gas through the liquid phase, right? It immediately solidifies, right? That is how you get those fancy aluminum coatings on your plastic cased computers, right? Ever thought about it? How they put aluminum on it, right? Would they inject a plastic on it, so that would have different behavior? Your aluminum metal is going to get deformed. And if you put heated aluminum on plastic, if you try to do the other way around, then the plastic is going to melt, right? There's a problem, right? So let's say if you have got this laptop which is plastic, right? Plastic, and you want to put aluminum on it, they're not going to stick. You cannot put glue, because glue can be removed. If you want this to be a permanent one, what you do, that you melt this down, right, to nearly gaseous level, right, very high temperature gas. You sputter it as a liquefied gas, right, or nearly boiling aluminum gas, right, and just spray it on this sheet which is dipped on liquid nitrogen, right, very cold at a minus 200 degrees Celsius, right. You take this sheet to this, and while this is at boiling point, right, about 1200 degrees Celsius or more, right. So nearly above this, right. Even at that level, if it's not purely boiling, then it is still so thin, right, so heated up that it can be sprayed on like a gas, right. So like fumes. So we just spray it on this, so the temperature is so cold that the plastic does not melt, and the metal immediately solidifies into a very fine finished, right, surface that is very smooth. If you put your fingers on it, right, it's a very smooth coating, right. So this is one way to use depositing, right. It's a very cost effective way compared to using very complex machinery to cut the sheet and to put it around and to paste it around. That's going to be very hectic problem, right. So they found a more economical solution using this method called deposition, right. And sublimation, we have the example of CO2, what we call as dry ice, right. It's a form of ice, right. It's not like water ice. This is looks like ice, right, but it is actually CO2 cooled so much that it turns into a solid, right. And that is what we call as dry ice. And once we let it in the air, it does not go into the liquid phase immediately at minus 50, 60, right. That's probably the average temperature at which you keep these, right, in the freezers, right. These packs are available in the market as well, right. You'll probably find those in the UK, right, on in some of those departmental stores or maybe tech stores, right. They would give you this CO2 pouches, right, that has cubes in it, right. We call that as dry ice. That's for storing something at a very low temperature, right, if we want to keep it, but keeping it away from water as well, right. So the CO2 is not going to damage your product, unlike water, right, which may react or may cause some rusting or on some components, or maybe some food article that might get spoiled taste due to water, right. So we can use CO2 over there, right, CO2 dry ice cubes, all right. Now these are the complex states of matter which you are going to now be concerned about. And for these as well, you can talk about the particle nature, right. From what to what is happening, right. The particles immediately get energy to flash directly into this breaking free point, right. Immediately they have a very small range in which they can do this, right. And the same way for the deposition, we don't give enough time for the particles to get come around loosely. They just stick to each other immediately, right. And in a very finite arrangement, which we call as deposition, right. Now are we clear about these states of matter and how the particle behavior can be related to it? All right. Now coming back to the periodic table now, right. Now let's talk about some of the behaviors that we have for these, right. As I said, these some of these, like these 17, they exist as gases, right. And then these 16 ones, they exist as gases, right, but the sulfur is a bit solid. But these are mostly gases related to one another, right, over these, and they have similar behavior, right. So why what is going to be the behavior, right, in general, right. So I'm going to give you two trends to remember, right, for now, right. For size, and for melting and boiling point, right? You can say physical properties for now, right? Just relating the physical properties, right? So the size of the atom increases downwards, right? Down the group we're going to call it, right? We let's signify this as size of atom increases, right? Uh, let's write the whole thing then. My apologies, right? So size of atom increases, and over here the melting and boiling point uh, increase in melting and boiling point, right? So down the group, the size of the atom increases, and from right to left, right? From right to left, uh, right to left, right? In that case, let's come back to this part table, right? So from this perspective, the size is going to increase, and this way the size is going to increase, right? The size. So tell me, which atom is bigger? Chlorine, which is 17, or potassium, which is 19? Which is going to be bigger? Sorry? Potassium. Very good. Okay, is carbon going to be bigger or silicon going to be bigger? Okay. Is hydrogen going to be bigger or helium? Hydrogen is bigger, right? So helium is the smallest atom, by the way. This is a fact that the smallest atom found in the universe is actually going to be your helium atom, right? Nothing smaller can exist. Hydrogen is slightly bigger than that, even though is supposed to be a smaller atom because it's got one proton, one electron, but still helium's got more nuclear pole, right? We're going to talk about that. How these positive, you do know that the positive and the negative charges they attract each other, right? So how these attractions are there, right? And how this affects the size of the atom, right? So we're going to talk about this once we go a little advanced into the topics, okay? Now for the melting point and the boiling point, now this is going to have further bifurcation as metals and non-metals, right? And I've marked the non-metals as yellow for you, right? For metals, it is going to I'm just going to draw the arrows, right? It will you can say the melting point increases up the group actually, right? And it if you talk about left to right, then we don't need to talk about general left to right, because this is only a group property, right? That means only group are going to depict that. The other groups are going to have entirely different behavior, right? So it is just up the group. And for non-metals, the melting and the boiling point increases down the group. For example, if I talk about chlorine, right? Then chlorine is about minus 39 degrees Celsius, right? It turns into a liquid, while bromine turns into a liquid at 25 maybe degrees Celsius, and iodine is pretty much a solid that is going to melt actually at about 79 degrees Celsius, right? So you see that as I'm going down the group, right, down the graph from fluorine to chlorine to iodine, right, or bromine, right, that is going to increase the melting point, right? So from low melting gas to a low melting solid it has converted, right? But for the metals the trend is opposite, right? That means potassium is going to be melting later, right? And lithium is going to have a much less melting point, right? So we can say, sorry, it is sorry, my bad, right? Potassium is going to melt earlier, and lithium is going to melt the least, right? So that we can say over here. So let's say lithium, right, it melts at 159 degrees Celsius, right? Sodium is gonna melt around, let's say, 78 degrees Celsius or so, and potassium can melt at 35 degrees Celsius, right, easily. So you can see that the melting point for metals is increasing. That means if you go down the group, it is decreasing, right? It's gonna decrease. It's the other way around. So they have opposite trends for the increase in their melting and boiling points, right? Now these are the basics that you need to understand. Over here we have related halogens, and by the way the similar behavior is going to be there, right? Like decrease, I'm just writing these greater so that you understand which one is actually having a greater one, right? For the, as I said, these are opposite trends, so the greater symbol is opposite for each other, right? This is going to be same for the group 1A, right? This is group 1 metals, right? Now for group 2, it's going to be a similar, right, trend. A little different, right, because the atom is now smaller. So let's say it's going to be like for beryllium, then it's going to be magnesium, and then it's going to be calcium, right? So maybe calcium can melt at 150 degrees, right? That's going to melt at 300 degrees, right? And that's going to melt at, let's say, 450 degrees. Now these are not the actual values, I'm just relating these are going to be similar, right? Maybe higher or lower than these values, but the pattern that I'm talking about, the trend, right, we call as, right, the trend is going to be as is, right? So you can check up these values on the internet, right, anywhere you want, and get to know these values, maybe listed in your textbook, or the text content, right? So you can compare what has been done over here, right? So are you clear so far how these are arranged? What are the general properties in terms of their size and in their melting and boiling points, right? And if we talk about the reactivity, right, which is the last trend we're going to talk about, right? So the last trend is reactivity. And what is reactivity? That I told you is the activity of the electrons, right? So the reactivity, we're going to talk about metals and non-metals, right? Basically in the periodic table, and when I'm drawing these arrows, I'm referring to where the element's position is in the periodic table. So generally this is the trend, right? So the reactivity increases in this pattern, right? So if, let's say, let me just draw a periodic table for you, right? A rough periodic table. Let's say if this was the periodic table for you, right? Like this. So sorry, right? My bad. Oh, okay. If this was your periodic table, right? Like this, the whole complete one, right? With the helium and then the hydrogen, right? So in that case, the metal that is going to be at this point, right, this X point, is going to be most reactive, and the metal which is going to be this way, right, that is going to be least reactive, right? Now for the non-metals, if I draw the same idea, right, and you do know that non-metals are only one side of the periodic table, right? I'm just gonna make this staircase, right, just to give you an idea that these are sorry, these are the only non-metals that are there, right? I'm gonna use let's say red one, right? So these are now the non-metals for you, the red ones, right? So these red ones are the non-metals, right? For them, and they actually, the trend is actually opposite, right? So it's gonna be like this, right? So up the group, or from left to right, the reactivity increases, right? So the reactivity of non-metals increases this way. That means this metal is going to be the most reactive one, right? This one that I'm circling, the most reactive, which is going to be your fluorine, right? Now let's talk about this trend as well, right? Let's make some questions. Okay, is calcium more reactive, or aluminum? 13. Good. Okay. Now let me know if lithium is more reactive or sodium. Okay. Is fluorine more reactive or bromine? Fluorine, because it's the opposite trend to the metals. Very good. Okay. Is oxygen more reactive or fluorine? Nitrogen and oxygen. Sulfur and oxygen. Okay. It's very good. Okay. Now magnesium or calcium? Calcium is more reactive. Very good. So now you have understood and pretty much mastered these trends, right? So just have a look at these. I'm just gonna share this recording as well, right? I'll put it there if you want to review this, any of these properties, and I can share these notes with you in the PDF form if you just want to have the written context of this. Okay? I'm not sure what kind of book you're using. Are you having book on the Chrome book? Are you using any book on that, right?